Heat transfer is energy in transit. It can be used to do work, and it can also be converted to any other form of energy. The first law of thermodynamics states that the change in internal energy of a system equals the net heat transferred into the system minus the net work done by the system. In equation form, it is delta U equals to Q minus W. Please note that Q is positive for net heat transferred into the system, and W is positive when more work is done by the system than on it. Here, the delta U is the change in internal energy U of the system, while the internal energy of a system is the sum of the kinetic and potential energies of its atoms and molecules. So it's related to the temperature of the system. One important characteristic of the internal energy U is that the internal energy of a system depends only on the state of the system and not how it reached to that state. In other words, the change in internal energy delta U equals to U2 minus U1 is independent of what caused that change, and it is independent of path. Let's look at this example together. In part A, we need to first find the net heat transferred into the system and net work done on the system. Then we can use the first law of thermodynamics. So the net heat transferred into the system is Q equals to 40, that's heat transferred to the system, minus 25, that's heat transferred out of the system. When it's out, we use minus. So we get 15.00 joule, and the net work done by the system is 10.00. That's the system does that amount of work, minus 4.00. That's that amount of work done on the system. So when it's done on the system, we use a minus sign, and we get the total work is 6.00 joule. Then, according to the first law of thermodynamics, we have the net change in internal energy delta U equals to Q minus W. We get 15.00 minus 6.00, and we have 9.00 joule. In part B, the net heat transferred and the net work done are already given, which is 150 for heat transfer and 159 for work done. But the key point here is the sign. This heat transfer is the heat transferred out of the system, so it's a minus sign. And this work is the work done on the system, and it's also a minus sign. So we get the net work transferred, if we think into the system, is positive, and then this is minus 150.00 joule. And the net work done by the system, if we think by the system is positive, then the work is negative 159.00 joule. And then we use the first law of thermodynamics. The net change in internal energy is, again, delta U equals to Q minus W. But this Q is negative 150 minus negative 159, and we have 9.00 joule. Now let's consider the work done by an ideal gas in some simple processes. In an isobaric process, the pressure of the gas remains constant. As shown in this figure, if the piston moves upward a distance of d, the work done by the gas is the force F times the distance d, and we have F equals to pressure P times the area of the piston, A. So F equals to PA. And since P is a constant, we have known that during our isobaric process, we can combine the A and D to get the volume change, delta V, so that the work done by the gas during this expansion is P delta V. And please note it's the isobaric process, so P is a constant. If we draw a PV diagram, so here's P versus V, for this isobaric process, we can see that the pressure P stays as a constant and the volume V changes. If the gas goes from state A to B, the net work done by the gas is P delta V equals to P final volume minus initial volume. So it's the volume at B minus volume at A, and that is exactly the area under this line of the PV curve. On the other hand, according to the ideal gas law, for constant P, we have VA over TA equals to VB over TB. So V is proportional to the temperature T. So that at state B, the gas should actually have an even higher temperature, TB, because the volume is bigger here. Since the internal energy U of a system is the sum of the kinetic energy and potential energy of its atom and molecules, the U is actually increasing when the temperature increases, so that we have the delta U is positive when the gas moves from A to B, because B is at a high temperature. And from here, we know the work done by the gas is also positive, because when the gas expands, it does some work to the piston. We have W is positive, delta U is positive, and we combined with the first law of thermodynamics, we have Q is also positive. So that we know during this isobaric expansion of the gas, it actually requires that the heat transfers into the system to keep the pressure constant. In an isochoric process, the volume of the gas remains constant, because isochoric means constant volume. Since delta V is constant, the work done by the gas is zero. According to the ideal gas law, for constant V, we have the pressure is proportional to temperature. We can combine the isochoric process of constant V with our isobaric process, constant pressure, to show that the net work done by a gas system depends on the path taken and not just the endpoints. As shown in this figure, if we consider from A to C, we can see that more work is done if we go from A to B to C than if we go from A to D to C. It can also be shown that if the system follows a cyclical path A, B, C, D, A, then the total work done is the area inside the loop. In fact, the work done in any cyclical process is the area inside the loop it forms on our PV diagram. Let's look at this example together to show that if the system follows a cyclical path A, B, C, D, A, the total work done equals to the area inside the closed loop on the PV diagram. To calculate the work done by the gas along each segment of the path, we use W equals to P delta V for the isobaric process A, B, and C, D. It is important to notice that from the state C to D, the volume actually decreases, so that the volume change delta V C D is negative, and the work WCD is also negative. For the isochoric process B, C, and dA, where the volume of the gas does not change, the work done by the gas are both 0. So that the total work done by the gas is all the 4 segments added together. So we have 750 plus 0 plus negative 100 plus 0, and we get 650 joule. If we just consider the area inside this rectangle A, B, C, D, A, the area equals its height times its width, which is the PAB minus PCD is the height times delta V is the width, and we get 650 joule. This is exactly the same number as we get from the total work in part A, and that improves that the total work is exactly the area inside the closed loop on the PV diagram. There are 2 other important processes on our PV diagram. One is called the isothermal process, where the temperature of the gas remains constant. As shown in this figure, if the piston moves very slowly and the whole chamber is in good thermal contact with a large heat bath, then the temperature of the gas system does not change during this process. We can draw a PV diagram for the isothermal process, and according to the ideal gas law, for constant T, we have P1 V1 equals to P2 V2. Since the pressure here is not a constant anymore, it is a little complicated to calculate the work done on the gas or by the gas numerically, and this is not required in this course. However, we can understand that if the gas expands isothermally from state A to state B, then the work done by the gas equals to the total area under this PV curve as shown in this picture. If the process is reversed and the gas changes from state B to state A, then the absolute value of the work is still the same area, but the sign is negative. One thing we can be sure in an isothermal process is that since the temperature does not change, the internal energy U is a constant, so delta U equals to 0. And combining this with the first law of thermodynamics, we have the heat transferred into the gas system Q equals the work W down by the system. The last process is called the adiabatic process, meaning there is no heat transfer during the process. Processes that are nearly adiabatic can be achieved either by using a very effective insulation or by performing the process so fast that there is little time for heat transfer. Temperature must decrease during an adiabatic expansion since work is done at the expense of internal energy. Combining Q equals to 0, no heat transfer, and the first law of thermodynamics, we have delta U equals to negative W, so that the internal energy decreases if the gas expands and does some work, and the temperature also decreases. At a specific volume, lower temperature results in lower pressure, so that if we compare the PV diagram of isothermal process and adiabatic process, the PV curve of adiabatic process is always below that of isothermal process.